All right, what do we have here? The answer is D. Lots of people said B. The answer is D. It's always the last path of this node, yes.
I'm not sure this question makes a whole lot of sense, because you don't calculate a heuristic for an arc in the first place. You calculate it for a node, right? And it would generally be the heuristic from wherever you're thinking you're going to.
I think you should have voted for E, but no one did that. Yeah, you're right. It should be the heuristic value for all the nodes in the path. But in any case, the closest one is D. The other one is just, yeah, look, let's make it D. D's the, you're certainly not adding up the heuristic value for all of the nodes in the arc. You're adding up the cost for all the arcs. You're certainly not adding up all the heuristic values. It really is the case that you have a start node, you have a path, and then you have some estimate to a goal. Here's the node. This is an estimate. And these are all the part, and this is the cost. The cost of the path, and this is h of n, and this whole thing is f of n. You can add those up. So it's you started from the start, you've got the end node here, we've got an estimate of the end, and then we're doing that. Okay. You should have got that one. Okay. One more to redeem yourselves. Which of the following is false? You might need more time here. All of the search methods based on the generic search algorithm can go on an infinite loop on finite graphs. B, heuristics in spatial domain have to be straight line distances. C, arc costs must be non-negative to make sure the least cost first search finds the least cost solution first. D, the complete search algorithms find the solution if one exists even in infinite graphs. And A star uses the cost of the path to a node as well as the heuristic information about the node. Okay. Which of those is false? All right. Good. Good. The answer is B. B is wrong. Let's have a look. A and D were both popular for being wrong. I was actually going to give a summary of these things. I thought it was much better to ask a question. So all the search methods can go into an infinite loop on finite graphs. We did this last time. This is a clicker question we did last time, remember? If we have a path, no path leading to a goal, right? If we have this graph that looked like this, we had a start node here, and we went to there, and then we sort of stopped. And we had another node, the goal node was here, but, sorry, the goal node was here, when is it? The start node was here, and this one just went into a loop, right? And if you started from the start, no matter which one you choose, there's always this infinite path we can go through. So if we start from here, we're trying to get to here, there are no paths to here, right? It doesn't matter which element of the frontier you keep choosing, you're going to keep going in this loop. You're not going to stop, as we've seen it so far. And D is a definition of a complete search algorithm. It finds a solution if one exists. Yes?
For D, is it the case that if the starting node has an infinite number of
Yeah, but we've defined a graph having. We only have a finite number of neighbours. You can. But this is the definition anyway. This is the definition I gave of a complete search algorithm.
Assuming that there's no node with infinite number of neighbors, right?
So we need to assume, yeah, we assume there's not an infinite number of neighbours. Yeah. I don't know if that was them. But B is obviously wrong. You don't have to be straight line distances. You can use all sorts of things. You can use highway distances. You can use all sorts of heuristics. You don't have to use straight line distances. Right? You can use all sorts of things. We could use a distance of one good heuristic in spatial domains, particularly for driving, is to actually assume you want to get to a highway and see if I traveled all the time on a highway, what would the slowest time be? What would the fastest time be? And then you can sort of do the straight line distance as well. Right? So you could sort of think about having a highway, a highway that goes around. Right? If you're on a highway, then you can go really fast. But if you're going on this other road, you can go slowly. Right? You could imagine sort of getting to a highway going fast might be one estimate, the other one might be driving slowly to the goal. And the minimum of those two, right, might be a nice heuristic. But they don't have to be straight line distances. We can use all sorts of things. Okay, any questions about that? All right, so let's look at today's. So at the end of the class, we're going to talk, so mainly we're going to talk today about cycle checking, multiple in path pruning. But first, explain the complexity of these things and justify why this monotone restriction is useful in A-star search. So let's try and go through this. All right. So just to make sure we're... So here is a graph that's sort of like the graph we saw before. We can go backwards and forwards on this A-star. This is like the one, if you're doing Google Maps, is going to do this. And if we have a goal down the bottom and we start stepping, A-star search is going to start choosing nodes towards the goal, and it's going to keep searching for other paths to this node. It's going to choose this MP. It's going to get, now all of a sudden it's going to keep choosing nodes, adding on these things. It's going to choose a whole lot of different nodes in some breadth first manner until it comes along like this, chooses this RM, which has a good one that finds this path. So it's really exploring multiple paths in order to find a goal down at AP. It completely ignored the things that were a long way away from the goal. Okay, so it's looking for where this goal is going. Okay, do you want to go through this more slowly? We did last time, but I just mainly wanted just to show you. So this has 14 nodes expanded, okay? Any questions about this? Do you want me to go through it slowly again? Slowly. No, yes, no. Okay. All right, play with it. This code here is available. We wrote it for you to play with, so please play with it and then come back with questions. Okay. All right. So let's try and form an argument that says if there's a solution, A-star always finds an optimal solution, and it's going to be the first path to the goal selected if number of conditions, first of all, is the one as pointed out here. The branching factor has to be finite. The arc costs have to be bounded above 0. So we're going to assume that there is some epsilon greater than 0 such that the arc costs are greater than epsilon. And we're also going to assume that h of n is non-negative and is an underestimate of the cost of the shortest path from n to a goal node. Okay, so understand what these assumptions are. We'll explain why we're going to make these three assumptions in a minute. So let's try and work out this proof of this. So let's suppose we have A star and we have a start node so we have a start node, and we have a goal, and over here we have a path, we don't know where it goes, that leads to a goal. So that's path P. So it might be some long circuitous route. But it's the first path found to a goal that's selected. And suppose there's some other path P prime. There's some other path P prime. Some other path P prime on this path. And a question that we want to know is, well, could P prime possibly lead to a shorter path to the goal, or is this the shortest one? Okay, so we'd like to know, is it possible that we could extend P prime to the goal, and so it's shorter? Right, because this is sort of exploring all of the paths to the goal, through all these initial paths we're exploring, and now we're going to ask if once we've selected P, is there a shorter path P prime? All right. And P was selected from the frontier before P prime was. So what does that mean? Why was it? So what does that mean, the fact that P was chosen before P prime on the frontier? So P was selected from the frontier before P prime. What does that mean? Why would that happen? Yeah. Cost of P is less than the cost of P prime. Is that right? Yeah.
Cost of P plus the heuristic of P is less than cost of P prime plus the heuristic of P prime.
Right. Right, is that right? Is that right? Who thinks that's right? Who thinks that's wrong? Who doesn't think? It's wrong, by the way.
We don't need the heuristic for that, right?
Why?
Because we already have the goal.
So what do we know about it?
0.
So this is equal to 0. This thing here is equal to 0. But that wasn't the error. That was just the aside. Yeah.
It's less than or equal.
Yes, thank you. It's less than or equal. Okay, so we know that. And as pointed out here, we know that h of p is equal to 0. Okay, does that make sense? Everyone happy? That's, I think, there. Now, h is an underestimate. So what does that mean? So the fact that h is an underestimate, what does that tell me about any path, say any path p prime? So p is going to go from here, and then it's going to continue along there, and it's going to go to the goal. So this is all p prime. So this, I should different color. So p double prime is the path from the start to the goal via p prime. So what do we know then about the underestimate? What does that tell me? Yeah.
The actual path might be longer that way than the heuristic suggests.
So what do I have? So what's the equation I'm going to write down?
The cost of P prime
Yep.
will be greater than or equal to the cost of P double prime will be greater than or equal to than the cost of P prime plus H P prime.
Right, because it's an underestimate. Does that make sense? Let's write the other way. I can write the other way around because it's easier. Cost of P prime plus H of P prime is less than or equal to the cost of P prime. If I put these two together, what do I get? If I put this and this together, what do I get? Oh, let's rub this out. I just rewrote it. If I put these two together, what do I get? Someone else. Yeah, you two answer everything. Come on, else. What do I get? Oh, if you have A is less than B and B is less than C, what do you know? A is less than C. Okay. What do we have? Oh, well, let's change. Let's make it closer to the problem. We have less than or equal to.
So, is it that cost P is less than or equal to cost of P double prime?
You should say it is the cost of P, not is it. Right. The cost of P is less than or equal to the cost of P double prime. Right? Does that make sense? Was it this that was confusing, or the fact you could use other formula for A, B, and C's? Okay. Does that make sense? Right. So the cost of P is less than or equal to the cost of any other path we could possibly do. Okay, so any other path to the goal has to go via one of these, something that's on the frontier. Okay, otherwise, because we're essentially exploring all the paths. So that's why we're going to have the fact the first one we choose is going to be the shortest one. Okay, questions about that? Right, so that's the first one chosen. If we choose a path to a goal, it's going to be the shortest one, but that doesn't show it's admissible. We also have to show that a goal always can find a solution. And the idea is that the frontier always contains the initial part of a path to a goal before the goal is selected. So if there's a path to a goal, the frontier always contains the initial part of a path to the goal. And it halts essentially as this cost function. As we keep going, this cost function keeps increasing. And it keeps increasing past the actual value, and so the cost plus h of p has to keep increasing. Right? Because h just adds it on. So once we have the cost of h of... So this eventually exceeds the cost of the path to the optimal path to a goal, and then we'll actually have to stop. Does that make sense? This thing, the cost of P, the cost of this P prime, it keeps increasing. Right, in finite amount of time, because there's a finite branching factor, it has to exceed the actual cost of a path to a goal. In which case, it's going to have, it must have selected the path. Right, we ignore H's, the fact that the path costs, the cost of paths keep increasing. Okay? So if we go back to this one here, we need the branching factor to be finite because we don't want to have infinitely many paths on there. What we don't want to occur is that they have to be bounded above 0 because we get this funny situation of we might have length a half plus a quarter plus an eighth plus a 16th plus 1/32 plus 1/64, right? There's an infinite path. And what is this approach? Yeah, this approach is 1, right? And if there's a goal, there's a path here which is of 2 here and 2 here to a goal here, and that doesn't approach the goal. Right, then this path here can have an infinite path with a finite cost. So you can have, if the path costs can be anything just greater than 0, you can have infinite paths with finite costs. And if h is not if h is negative, this whole argument falls apart. Right, this one here might be. And if it's not an underestimate, then this argument falls apart too. All right, questions? All right, so it's a useful thing to know. When we find a solution, we're going to find the first one to it. All right, questions? Questions? All right. Next question is, how do good heuristic help? Suppose C is the cost of an optimal solution. What happens to paths P where the cost of P plus H of P is less than C? What's going to happen in A star search? Okay, you can answer. What happens?
It'll keep exploring the path even though, so the heuristic thinks the path is shorter than it is, and it'll keep exploring that path even though it won't actually.
Right, every path P with this property gets expanded. Right, so if it's less than this, this is going to be selected before we select the optimal path. So it's going to expand every path of this form. And what about these ones? What about the ones that are equal? Well, it's going to expand some of them until we found a solution. So it's going to expand it expands all paths where cost of P plus H of P is less than C. It expands some of the paths where cost of P plus H of P equals C. And what about the other class? What about these ones? Someone else? Yeah. Yeah, expands no paths where this is true. So it expands no paths with the cost of P plus H of P is bigger than C. So now this will tell us why it's going to, a heuristic function helps. How can a better heuristic function help? What's it going to do to these classes of things? Yeah.
With a better heuristic function, we're going to have more of the third case than the first case.
That's right. If the heuristic function is better, we're going to have more of this case. Right? That's what we'd like. So we'd like more of this case. As the heuristic function gets bigger, we're going to have more of these things. right? A better heuristic function is a bigger heuristic function. So a better heuristic function is larger. We'll have more of the third case. Okay, because as we increase h, it gets more informed, and so this class of here is going to increase. What can sometimes happen is that we might reduce this, but then we're just essentially randomly selecting some of these paths. So some of the times, although we might reduce this, we might, if this is a large class of paths, sometimes it might be faster. It could slow us down because although it reduces this, it could make, just by random chance, we're going to choose different elements of this. So if you want to check it, you should be aware of this. Okay, questions? Okay. How am I going? All right, so here's the summary of the search strategies we've seen. So we have, this is what we had last time. We had depth first is not complete, breadth first and lowest cost first are not complete. None of them halt. Depth first search has linear space. So what happens for best first search? What are the answers in there? Is it complete? Who remembers what it was? Is it complete? No. Okay. Does it halt? No. The space is exponential, we did. What about A star? Is it complete? And it doesn't halt and its space is exponential. Okay? Questions about that? All right, so now what we're going to look at two methods to actually make this complete. So if we have a cycle like this, what we'd like to do is we'd like to prune a path that ends in a node already on the path. So if you have a path like this, we're starting up from S, the second node down, we don't need to expand it the second time around, so we can get rid of this loop. Okay, so we just get rid of loops. Right, if we just get rid of loops, we can reduce the amount of search we're going to do. So this is called cycle checking. So we're going to prune a path that already ends in a node on the path. So here's the algorithm. It's very simple. It's just my generic search algorithm. It's just got one test in the middle. And it just says, well, if the last node on this frontier is already an element of the set of earlier elements, I'm going to throw it away. A very simple modification to my generic search algorithm. And otherwise, I'm going to do exactly the same. I'm going to check it for gold and expand it. Okay, does that make sense? That's pretty simple, right? If it's a cycle is when nk is an element of it. And if it's a cycle, I'm just going to throw it away. Okay, questions? This should be reasonably straightforward. Okay. So let's have a look at what happens in this graph here. Let's reset this. And I've forgotten how many it took before. Let's count it. 1, 2, 3, 4. I'll just keep clicking and it does all of this. This is without it. And it does it 14 nodes. And if I turn on loop detection, in here it's called, and I'm going to reset it, and I'm going to step. What it's going to do is it's going to still look at these things. It's going to choose KD, then it's going to choose MP, and then it's going to choose JB and KD, and it's going to wander around. But what it's not doing, it only expanded 9 nodes. So it didn't ever go backwards or forwards, and it never went around in the cycle. Okay? So now I've reduced the amount of nodes that I'm doing, because I'm just not looking when it goes backwards and forwards, because that seems to be a waste of time. Okay, any questions? All right. So if you're doing depth first search, checking for cycles can be done in what time? How quickly can we do it? Constant. You can actually do it in constant time. Because all you need to do, if you're explicitly storing the nodes, we just have a bit whether it's on or off. And when it's in the path, we just turn it on. As we go off the path, we backtrack and turn it off. So we just need one bit in every node. You're saying, is it in the current path? And as you go back, you can undo it. So it turns out you can do this in constant time. So you can do depth first search. You can do it in constant time. So for depth first search, cycle checking, for depth first search, we can do in constant time. And we just need one bit for every. And this bit specifies, is it on the current path? You know, it specifies it has 1 if it's on the current path, and 0 otherwise, if it's not on the current path. This is assuming that if the nodes are explicitly stored. Which you've never really assumed, but if we're not, we can do it in just a set. We can do it in log n time. All right. What about the other methods? Turns out this doesn't work for breadth first search or for A star because there's not one current path. And it turns out that if you have multiple paths we're doing, if you're maintaining multiple paths, cycle checking requires a linear search. Okay, so for other methods, cycle checking is linear in path length. Because you can't do better than going up here. You can imagine having some data structure test this set, but then you have to, when you split this, you have to mess up the set. So it requires linear time. Questions? Okay. So with cycle checking, which of the algorithms halt on finite graphs? Oh, sorry. But there are multiple paths. For this path, you want to have a different answer to this path. So this is a path here. And if you're selecting this path, you don't want to say yes to this node. So if you're doing this one, you only want to say yes to these 3 nodes. But when you move to this node, you want to say yes to those nodes. You have to find them. You can't. But this one here, if you've... Sorry? Oh, that's a good question. We'll get to that in a second. That's the next method. Yes. But this one here, you can't. Yes, precisely. We'll get to that. But let's do this other one, answer this question first. With cycle checking, which algorithms halt on finite graphs? Okay.
About depth first search.
Yep.
What's the data structure for storing the path?
here you can just use a stack. You can actually just do a stack of all the nodes. And as you take things off, you can, essentially the nodes that are on the current path, you just need to look at their neighbors. Just a stack. But you know which nodes are actually on the current path. There's sort of only one stack. Right, but there's sort of multiple paths being stored here. At this point, the point of this one is only one path being stored.
If it's a stack, how can we know that it's a cycle constant time?
Because for each node on the thing, we know which elements we know. There's only one path we're looking at. Right, so we know we're on this path here. We can make a bit for this. The other nodes are these other. Right, we have this current. There's only one. Essentially, there's only one current path. There's only one current path. Right, the neighbors are this, and as we get to this one, as we backtrack, we've got to undo the bits for these and go to this one.
So we need to backtrack, right?
Yes, you need to backtrack. You need to undo them. It's not.
Doesn't that take linear time?
No, because you're only backtracking up this path. As you add them, you're going to do constant time overhead, but as you backtrack up, you've got to undo the bit, and reset the bit, undo this bit, and set this bit. But it's still only still constant time. It's just a constant overhead. It's just an extra step you have to do when expanding this node. There's an extra step when you go back as well. When you expand it, and when you go back, you have to do something. Oh, it's a fun exercise. I didn't get it. Yes?
If the graph is twice as large, then it's going to take more time to search each node. So
It's only a constant time more for each node. It's only a constant time more. It doesn't matter how long. This argument, it doesn't matter how far above this is. Right? You can imagine that enormously. As you keep going down here and changing these down here, it doesn't depend on how all the rest of the stuff up there. It's only local to here. About what bit we're sunsetting bits. It might be complicated here, but it only depends on how far we're backtracking. It doesn't depend on all the rest of the path we're in. There's another argument as to why it's linear. Yes, because you backtrack here to the constant time, because we have to go down there anyway. When we go up, we're going to do something. So with cycle checking, which algorithms halt in finite graphs? Someone over here said an answer. I heard an answer. All of them. Right? If you have a finite graph, there are only finitely many paths without cycles. So the answer is all of them. Okay, so all of the algorithms we've seen so far halt on finite graphs with cycle checking. All right, let's do the other one that was suggested. Is multiple path pruning can prune a node to a node n that the search has already found a path to. So if you've already found a path to a node, so you've already found a path to that node on the bottom there, any other subsequent path, we can prune it. So you only need to find one particular path to a goal. Okay, so for any node we found a path to, we can prune the other ones. If you only want one path, so here is these. So what do we need to store? Yeah.
I have a question. Suppose you're using A star for that graph. Would that algorithm find the path to that node in the least cost?
We'll get to that. Not necessarily, but it's going to. We're going to make it, so we're going to try and make sure it does. But what do we need to store? Right. So we just need to set a set of all nodes that are on some paths. Right, if a node's been expanded or visited, we'll write down we need to store a set of nodes that have been visited. Okay. And it's actually lowest cost first search with multiple path pruning. You've probably seen it's called Dijkstra's algorithm. So here's the algorithm. So someone asked about Dijkstra's algorithm, how it relates, but it has multiple path pruning. So what they do is a set of visited, and after we've selected visited as a set of nodes, we're going to select and remove a path from the frontier, and if the end node hasn't been visited, we're going to add it to the visited set and continues. That's the only thing we're going to do in here. Okay, so we just have a set of all the nodes we visited, and if we have a node, and if the end of the frontier is not on the visited list, we're going to throw it away. We've already reached it. And if it's not on the visited, we're going to add it to the visited list and continue. Okay? And if you do that for, if you do that for this, and if we do multiple path pruning, we're going to reset the search. We're going to step 1, 2, 3, and it's going to find it in 7 nodes. The other was a lot less. Okay, because we don't need multiple paths. Right, we don't need multiple paths to the same node. Except maybe it's going to not find the shortest path. But we'll do that next time. Okay, questions? All right. Okay, let's stop there and we'll talk about how to guarantee that we'll find the best path even with multiple path pruning next time.